1973 and later 1979 was a bad year for civilization. The short answer is oil got very, very expensive, and this caused quite a lot of problems for quite a lot of people. In 1979, Saab Valmet, as a partnership between Swedish carmaker Saab and Finnish industrial conglomerate Valmet, made a very special version of Saab's Model 99 that could run on two fuels, gasoline and either kerosene or turpentine. The 99 Petro, as it was known, wasn't very successful. Kerosene prices rapidly increased and the turpentine never panned out. However, was the use of turpentine as a fuel a reasonable idea, or was it an oil crisis gimmick? Today on Let's Wade Through, we'll have a look at turpentine as an engine fuel. What is turpentine? Turpentine, or terps, is a liquid product made from pine tree species and their relatives. Terps is a byproduct of some industrial processes involving wood. The largest of these sources is paper milling. Remember Valmet from earlier? They continue to be the leader in Finnish paper production and, by extension, of turpentine. Naturally, a supplier of turpentine would team up with a car manufacturer to try to build a car that could use turpentine as a fuel. What makes a good fuel? It's only appropriate to have a look at what's considered good fuel characteristics for both gasoline and diesel engines before we have a proper study of the turpentine. To do this, we need to take a quick detour down engine lane. Gasoline engines, technically called spark ignition engines, use a small but powerful spark to ignite the fuel vapors. Diesel engines, however, use a completely different method based on adiabatic compression. Adiabatic compression is the rise in temperature from the compression of a gas where the change in temperature comes only from the compression of the gas. They are called compression ignition engines. The air within the cylinder space is compressed so quickly that the temperature of this mixture spikes and jumps above the auto-ignition temperature of the fuel. The fuel is injected and it spontaneously combusts. These two methods of fuel combustion dictate everything else about the engine. The fuel used for each engine must be designed to accommodate each method. With fuels, knocking is the term used to describe the premature ignition of fuel when caused solely by temperature. This happens when the piston is still rising within the cylinder. Knocking can be a disastrous problem to have. Adiabatic compression happens in both ignition engines as both involve a gas and compression. Compression ignition engines require a fuel with a higher flash point to resist vaporization until the heat generated by the adiabatic compression coincides with the correct piston position to create useful combustion. The flash point is the lowest temperature at which a vapor forms an ignitable mixture. However, it also needs a low enough auto-ignition temperature so that the vaporized fuel will nearly immediately combust and, when timed correctly with the piston, push it back down to provide power. Gasoline engines require the opposite characteristics. As the ignition is caused by a spark, the fuel needs a low flash point to create enough vapor in the cylinder to allow for combustion. And the auto-ignition temperature must be a lot higher to allow for predictable ignition by the spark. Then, what does this mean for the usefulness of terps? Would terps work? The problem is turpentine isn't generally that good of a fuel by itself. For electric cars, it just makes an awful mess. Please don't try it. Gasoline engines require a wide range of different flash points within the fuel to allow the fuel to burn at a range of temperatures. It's the vapors that combust instead of the liquid. To start an engine in the cold, a fuel must have enough highly volatile components to vaporize and initiate combustion. In other words, there must be enough components of the fuel with flash points less than the temperature of the engine. The heat from combustion then vaporizes slightly less volatile components, burns that fraction of the fuel, and the process continues, adding more heat until the entirety of the fuel is vaporized and consequently burned. Gasoline's flash point is around -45 degrees Fahrenheit. Turpentine is about 100 degrees Fahrenheit. Pure turpentine, therefore, is a poor choice for spark ignition engines in cold climates. Hang on, you might be thinking, then why did a Swedish carmaker from Sweden develop a car powered by a fuel that can't start in cold weather? This puts the light on turpentine's usefulness as a fuel. It's best used when in combination. The Model 99 Petro used gasoline to start the engine and the turpentine to provide the bulk of the energy for actually moving the thing. The flash point of gasoline allows it to start an engine in the Scandinavian cold, while the turpentine is more than capable of combustion in a warm engine. There's other odd quirks to turpentine, such as its more rapid burn rate and the consequential generation of much higher pressures within the engine. This is a matter of engineering, and one that's already been solved. Turbo superchargers, or turbochargers for the layman, by their nature increase the pressures within the headspace of the cylinder. Turbochargers are already most of the way there to using a theoretical turpentine-based fuel. Turbochargers on gasoline engines are less than common and only work at certain engine speeds. To provide their power-boosting effect to an engine, they must first reach the speed of the engine. Gasoline engines typically operate in the range of thousands of revolutions per minute. That's quite a bit of speed the turbocharger must pick up. Now, if only there was an engine that normally runs at slower speeds. That's right, there is, isn't there? It's compression ignition engines, i.e. diesel. Diesel engines have much slower engine speeds than gasoline, roughly an order of magnitude. Turbochargers on diesels work better because of this. They also make diesel more competitive with gasoline engines by improving power, torque, and fuel efficiency. This is why automotive diesels commonly come with turbochargers pre-installed. This is where turpentine really shines. As a fuel additive, the switch from diesel to turpentine blended diesel would be less expensive than the equivalent switch for gasoline. Surprisingly, turpentine works very, very well in compression ignition engines. A paper from Lithuania looked at the environmental effects of a 5% terps blended diesel. Their results were rather unexpected. This blend of diesel reduced smoke emissions in a normal engine by between 7 and 20% depending on engine load. The only difference was the fuel. Anyone familiar with diesels or have been behind a large industrial vehicle on the road are quite familiar with diesel's tendency to burp and bellow. A paper out of India helps to explain why this effect takes place. They looked at a more complete emission profile with a variable blend of turpentine with concentrations up to 75% over a range of engine loads in a type of diesel known as a dual-fuel engine. These engines are configured so that the primary fuel, here turpentine, is fed through a manually adjustable carburetor, and the pilot fuel, conventional diesel, is fed through the normal fuel system. The turpentine can then be adjusted for study. They found that turpentine greatly increases carbon dioxide emissions while lowering carbon monoxide and smoke. This is known as a good trade-off. It also improved torque under load by 7%. The paper presents the speculation that turpentine improves the combustion efficiency by improving the volatility of the diesel and encouraging the formation of smaller droplets of aspirated fuel. As with anything, there's a trade-off when using turpentine with diesel. Nitrous oxides emissions increased along with unburnt fuel. Above concentrations of 75%, the turpentine produced more smoke than the diesel. It cannot successfully function as a fuel by itself. It must be blended to have use. Think of turpentine as a bit of an extrovert. It functions best with other fuels. Wood turps work as a fuel additive in gasoline engines. It shares similar characteristics to gasoline, including boiling point heating value and auto ignition temperature. Chemically, it appears compatible. Practically speaking, however, probably not. The problem is, the lack of research makes this a hard question to answer. Terps as a producible fuel additive. The one major benefit of turpentine over other biofuels is that it quite effectively ignores the fuel versus food question of conventional biofuel production. Agricultural resources are diverted to the production of ethanol through various plant-based pathways. In Brazil, this is famously done through the cultivation of sugarcane. In the US, this is more familiar as ethanol derived from corn. As modern agriculture relies heavily on petrochemical fertilizers, ethanol is still strongly linked with fossil fuel consumption. The problem is the scale. A cord of pine, about 2 tons worth of wood, only supplies about 10 gallons of turpentine. This is known as not very efficient. To put this into perspective, the number of Christmas trees cut down in the US is around 30 million. If all of these trees were to be used as a turpentine feedstock, the net result would be roughly 3 million gallons. The amount of diesel used by American truckers measure in at a voluminous 37 billion gallons. Blended in at 5%, the entire cut stock of Christmas trees could only supply about a day's worth of supplementation. Christmas trees do not have the same scale as managed forests, however. For example, managed pine-type forests in Virginia have yields of between 60 and 216 tons per acre, depending on soil quality, over a 25-year harvesting schedule. At best, an acre of forest can provide about 280 gallons of turpentine once every 25 years. This is a measly average of 10 gallons and change per year. 1 acre isn't impressive, so let's take this to size. The 7 or so million acres of pine in Virginia would yield 1.9 billion gallons of turpentine over 25 years. To supplement the U.S. diesel demand, an amount of 1.85 billion gallons of turpentine is required. That comes out to a minimum requirement of 160 million acres. Taking production losses into it, the grand total of forest area is a whopping 320 million acres of high production pine. That's an area twice the size of France, or 320 times the current area of Christmas tree production. As useful as turpentine is as a fuel additive, well, there's really not enough woodland in the U.S. to even attempt such an effort.